Hello and welcome back for another presentation in your online geography course. This presentation is mapping the Earth, looking at grids and projections. So although this is a longer presentation, it's very important because it covers a lot of incredible content that really sets the foundation of geography as a discipline. So I picked this map just because I thought it was really neat. It's one of the original Auto Club of America, Southern California maps of 1916, showing Los Angeles and San Fernando Valley. This is a map. That's what this is about. How do we break apart a round globe and turn it into a paper map? How do we understand that? How do we create a grid system? How do we create location and place and space? And that's really what this is going to be about. So we'll be introducing, again, latitude and longitude. We'll be looking at map projections, and we'll also be wrapping up with some other ways that we can look at the grid system on our Earth. So before we begin, we got to go back to this guy, Eratosthenes. We talked about him in an earlier presentation. So after measuring the angles of the noon sun, which is when the sun is at the zenith is at the highest point the sun will be in your vision in the sky, he was able to then divide the globe into a system of meridians and parallels. So after extensive study, what he did here first, looking at this diagram, this is our Pythagorean theorem in a sense. We're measuring a triangle. We have A is going to be our angle at the middle towards the Earth. S was a well in Cyan, and then A was a well in oh my God, Alexandria. Oh my, brain fart. In Alexandria. And so by looking at these two wells at the same time and within two different locations and making those measurements of the angle of the shadow, you're able to calculate the angular distance and difference between them. Well, as he continued to study this process, he was able to identify that the Earth was at a tilt. He was able, actually probably one of the first really, to identify that there was a leap day and that there was a correlation with very specific lines of latitude and seasons. So, fun fact, Eratosthenes used a measurement of Astates, which is an ancient Greek measurement. We really don't know a whole lot about it. We have figured that an Astate is between 150 and 210 meters, but it's very ambiguous as to what the real value is. So that's why when they said that he was the first to measure the circumference around the Earth, it's estimated that he measured it to be between about 24,000 to 29,000 miles in circumference. So it's a very, very large variation, but nonetheless, it was very good for being in a position where we couldn't even travel the world quite yet. So that really started this idea that we have a grid system, much like we view an Excel spreadsheet. So let's start looking at this. So this is the grid system. The first one we have is latitude and longitude. So this is a grid system that we use, much like Excel, that has X and Y axes, and then we're able to pinpoint a particular location. So it says here, the geographic coordinate system enables every location on Earth to be specified by a set of numbers, observed as either a decimal or in a different system known as degrees, minutes, and seconds. So this here, this is broken up into degrees, minutes, and seconds, which is most commonly used on maps, which are more large scale because the features are much larger to view. Smaller scale, when we look at like a map of, the United States, we would probably use decimal. It's a lot easier to use, but computers calculate that. It becomes too complicated. So perhaps this looks familiar to some. So what I did here is on Google Earth, this is a picture of the College of the Canyons, and then I overline these black lines to show your grid system. So this is a block. This is obviously the grid system that is on our planet is not actually on the surface. It's a set of measurements that we use, but this is what it would look like if it were to exist. Something that you'll notice is that they are all squares, but as we get farther away, north, the squares, they look like they're kind of tapering a little bit, and that's because they are. We'll talk more about that later. But nonetheless, we could pinpoint a location of where this car is, and we would know exactly where it is. I could give that data to someone. They could type it into Google Earth or Google Maps. They'd be able to zoom right in and know exactly the location of that car. Crazy, right? You use it all the time. You just don't realize it. It's in your cell phones. Your cell phones uses all that data. It's pinpointing your GPS coordinates. So that being said, the data of the grid system is used to understand the landscape, both as a two-dimensional piece, but also we can look at it in 3 dimensions. So this is obviously, this presentation as a whole is on your monitor. It's 2 dimensions. It's flat, but there's depth to it. There is an angle here. There are some 3-dimensional features with these buildings. So we are able to not use just the X and Y axis. We can also use the Z axis, which is depth. So if you think about it like a 3D printer, 3D printers print X and Y, which is a flat, but it can also move up and print height, the height itself, and that's your Z axis. So we can use that to create 3-dimensional models, which is essentially what's used in video game design. So moving into latitude. So latitude latitude's like a ladder. You climb up a ladder or you climb down a ladder. These are lines that wrap all the way around the Earth. Our starting point will be the equator, which cuts the world into 2 equal hemispheres. This will be our 0, like a protractor. So this is 0, then we can, like a protractor, use and measure our angles 0 all the way to 90, where you have a right angle. That being said, measured from the center of the Earth, latitude measures at 0 degrees at the equator and a maximum of 90 north or 90 south. So what ends up happening is that you're at your horizontal plane at 0 and you measure your angle. Maybe we'll say this is 45 degrees an angle. Once that angle is measured, then it's like a pen. It spins all the way around and draws a disc. That means no matter where you are on the line that I'm drawing has a value of 45 degrees from the equator, right? So that's north, or it can be in south. That being said, these lines are discs that wrap all the way around. They're discs, so it's a line that goes all the way around, and I'll explain what that looks like in a moment. They're also parallel. They're known as parallels because they never touch, they never cross. They're perfectly parallel from one another. Now, another thing that's interesting about lines of latitude is that if they're discs, right, it's a line that goes all the way around the surface of the Earth, the distance around them as you get closer towards the poles becomes smaller. So that being said, I think of these lines like pizza. Who doesn't like pizza? These are discs that wrap around the Earth and measure from the center of the Earth, going out, up or down. Then that line is drawn on the surface of the Earth. This is 45. This is maybe 90 degrees. It's a smaller disc. So I think of it like pizza. Maybe you've seen one of these before. This pan here represents the equator. Maybe this one up here represents 60 or 70 degrees north. As you get higher on the globe, those discs become smaller. The distance around the Earth becomes smaller. If you've ever run track and field, think about it. Professional track and field, everyone's not in a straight line. They're staggered, right? Because the guy on the inside has to travel a much shorter distance than the person on the outside that has to travel a much larger distance. So we stagger it for track and field. Same idea here. So we have these 2 types of circles that we identify. You have great circles and small circles. Great circles, well, the only great circle we have in latitude is the equator. It's the greatest circle around. It's the greatest measurement, okay? Everything else is smaller, right? It's smaller than the equator. So that's what this little table kind of puts in perspective, is that if you're at a great circle, or in this case, the equator, every degree that you travel along that line is equal to 69.171 miles, or about 111 kilometers. So if you move up to, we live at 34 degrees north, so we'll just say 30 for, just for our cases here. So we can see the distance on our line if we travel, along that line of latitude. Remember, it's measured going north or south, but the lines wrap all the way around. So if you're traveling from, 34 degrees north and you want to travel towards the east coast, you would travel on that one line of latitude. Every degree is now 59.956 miles. So it gets smaller until you get to the North Pole, which is a point. There's no distance. You can literally stand at the North Pole and just spin in a circle, and you technically walked around the entire world. Crazy, right? So we can use these values to actually calculate distance, right? So if I wanted to, if I wanted to measure the distance around the Earth, well, I know the Earth as a complete circle is 360 degrees. So if I want to go 360 degrees, and at the equator, it's 69.171 miles per degree, I just multiply those 2 numbers, and I get 24,000 and change. So you can do it that way. if you want to say, well, how far around the world is it at 30 degrees north? Well, it's 360 degrees all the way around, but each degree is worth 59.956. You multiply that and you'll see it's significantly less in distance. So, something to think about. Longitude. So longitude are meridians, which means that they are half of great circles. So ideally, although the Earth is an oblate spheroid, for our purposes, we understand that if I wrap a string around the equator, and I grab that string and I tilt it this way so it touches the North and the South Pole, it should still be taut or tight. So these are half of great circles because they intersect. They all intersect at the North or the South Pole. Now, again, measured from the inside of the Earth, this time they go east or west. And then once you measure your angle, the line is drawn going up and down to create that angle. Okay? So that's why. So here we have, this is 0 at the prime meridian. So this is 0, and anything going this way, you can see it's a negative number, which means you're traveling west. And this is positive, which means you're traveling eastward. So these are in 30-degree increments. So this is 0, 30, 60, and you work your way across. Actually, these are 15, sorry. 15 degrees, 15, 30, 45, 60. But nonetheless, so you have this grid system, perfect. Lines of longitude or meridians are half of great circles. Something that we notice is that the height of these are all equal because they're part of a great circle system. But see, this diagram here is also showing your lines of latitude. Look at the distance between them. See, again, we go with that idea that latitude, as you get closer towards the poles, the distance around the Earth becomes smaller. That's why these, as you can see, these meridians, these lines of longitude, see how equal those squares look, nice and big and perfect? Then as we get farther north, the distance between the meridians, the distance between the lines of longitude are being forced together until they intersect very tightly up in here. That being said, the distance between the meridians also will decrease as they get closer towards the poles. And why is that? Well, because the circumference of the Earth also becomes smaller. So when I think of this, I think of oranges. Why? Well, because they all intersect at the top and the bottom, where it was connected to the tree and where the flower was. And you peel the orange, and now you've got these beautiful half circles or slices or meridians. Okay? But can you peel an orange perfectly so it looks like a square map? No, you can't. We cannot. You're not going to sit there and peel an orange and make a perfectly square map. It doesn't work that way. The best you could do would be something kind of like this. And that's not really that perfect. You don't see people rolling out maps that look like this. Well, that's where we come into this idea that there must be some form of distortion. To make a map like the one behind me, there has to be some form of distortion. There has to be an agreement of what is important, what is not as important, and how do we smudge it and squish it and stretch it to make it look right. So simplistically, we can put it together. Latitude and longitude. So this is now a map. You notice that this is a projection of the entire world. Perfect. All of our major continents are there. We obviously see that Antarctica got, well, we'll talk more about that. It doesn't get on the map all the way because there's been some distortion in order to make things work out right. In the reality, looking at this continent here, this continent is the same size as Brazil in the real world. But as you can see, right now it's the same size as South America. But nonetheless, we can play with this and go, well, what if I want to know the location of point B? Well, here's my line of latitude. I see that it is on this line, which is 60 degrees north. Perfect. Then I can grab my line of longitude and see that it's on 120 degrees west, west of 0. So therefore, the coordinate for point or station B would be 60 degrees north and 120 degrees west. Well, what if I wanted to measure, and I'll put this back down here to 0 so we can kind of start fresh. What if I wanted to know the location of letter C? Well, I can do the same thing. It's also on 60 north, but this time we see it's on 60 degrees east. It's east of the prime meridian. Again, the prime meridian is going to be 0. It runs through the Royal Observatory of Greenwich, England. And if you ever get a chance to actually go there, it's pretty cool. They have a big laser beam that shoots out of the observatory and shoots a line as far as you can possibly see. Because it's literally a line that you could be like, well, I'm east or west, and go back and forth. It's pretty cool. Let's try letter D. Well, Letter D is here, so it's between 0 and 30, so it's 15 degrees north, and it's also going to be 45 degrees west of the prime meridian. So we are in greater Los Angeles. We're about there, about 34 degrees north and about 118 degrees west of the prime meridian. That's approximately our location. Now, these are using whole numbers. As mentioned before, we can use both a decimal system to get really, really specific, or we can use a system of degrees, minutes, and seconds. There's additional videos on that, but the idea is that instead of using larger values, we can take a degree, much like we would use a clock, but it's not really associated with time. We can take a degree and we can subdivide it into smaller pieces. We can say, well, 1 degree is equivalent to 60 smaller pieces called minutes, and each one of those minutes can be subdivided into 60 smaller pieces called seconds, right? So, as an example, you could say that, this location is 30.5 degrees. Or it could be 30 degrees in 30 minutes, because 30 minutes is the same as half an hour, or 0.5. But again, there'll be more on that later, and there's additional supplementary videos for your help with that. But this is just kind of trying to put the big picture together. So now I've mentioned this map is not right. We can see, again here, this is what it should look like. This is a globe. That's a perfect projection. How do we project the world as a map? Well, in cartography, a map is a projection that essentially takes a round surface and makes it flat. And the problem with that is that there is going to be a question in the integrity of the data. Have you ever photocopied a large book, like a page out of it? The book kind of bends a little bit where the seam is. When you make your photocopy, the area that's not touching the glass on the photocopier becomes distorted. The words get really big. It becomes skewed. There's been distortion, right? So that's what happens. The closer to the point of tangency, which is where, in a photocopier sense, that the book is touching its tangent to the surface, that's the most accurate. The farther away you are from that, the greater the distortion, the greater the error. So think of taking a, this is my photocopier, and this is my piece of paper. If I make it nice and flat, that's a perfect copy. It's a replica. But if I make a photocopy, but I'm holding the paper like this, the part where my fingers are, that's going to be accurate. But the farther we get away from that glass, the more skewed the information is going to get, the more inaccurate it will be perceived. There's lots of different ways we do this. We're going to talk about these 3 particular ones. And we've got planar, we also have conic, and then cylindrical, which the name itself depicts the tool in which it was used. So the way that this is done is, imagine you have a globe made out of glass, and everything's been traced on there, and you put a light bulb in the middle of that globe, turn the light on, and it projects like a projector, and you projects onto a piece of paper. Maybe the paper is wrapped as a cylinder. Well, and then you can trace everything on there. Everything closer to this red line is accurate, because that's touching the paper. As it gets farther north, you see there's space. That's going to create distortion. That's why, looking at this map here, we can see that this area here is perfect squares. Everything looks right. The farther north we get, look what happens to these places. Greenland's the same size, and actually bigger than South America. And then here we have, Antarctica, which is landmass-wise bigger than everything combined. There's inaccuracies. There's problems there. This is a good way to make a map along a great circle. We use a cone to make maps along smaller circles, and then we can use the azimuthal or planar projection to do points. So let's look at each one of these a little bit more specifically. So here's a projection called the Mercator Projection. It's a cylindrical projection. So this was actually designed by a cartographer named Mercator. He created this projection by mathematically projecting a vertically oriented cylinder along the equator. This was designed specifically because of travel. Navigators use this because a straight line on this map is generally a straight line when drawn by your boat if you're trying to navigate through the oceans. Google Earth uses this projection because it makes it much easier to zoom in and out, because a right is a right. There's really very little variance, but the reality is it's not a good projection because, yes, the shape is well defined. The shapes are perfect. The shapes of the continents, things along that line, but the size, the area is very inaccurate. So look at this. We use this as an example. These little orange balls, they should all be the same if this was on a globe. But what happens is you get farther away from the equator or the point of tangencies, these become larger. Notice how they're perfect circles though, right? So that means that the shape of everything is going to be well preserved. They just get bigger. Moving forward, we can look at a conic projection, which is great along a small circle. So maybe this is that small circle, which happens to be a line of latitude we're making a map on, known as the equal area projection. This is best for looking at maps along going east or west because there's no distortion going that way. But overall, it's a pretty crappy projection because look at everything else. Look at what happens to the circles. As you get farther away from that point of tangency, they're getting stretched and distorted and squished. They're getting stretched and squished. So you're losing all of the integrity. I mean, Antarctica is this itty bitty little taupe-colored line that wraps all the way around. It doesn't make sense. But it does if you're making a map just along this line. Other than that, it's not a very valuable projection. Well, what about azimuthal, which is a planar projection or a point? That is where that point was made on a projection. As we get farther away, look what happens to these circles. So they're trying to put everything on this round map, which is a flat surface, but again, you lose that information. So it's a projection that plots the surface of the Earth using a flat plane. This is what the Earth would look like if viewed from thousands and thousands of miles away from a spaceship. So it would look fine, but you would see it looks kind of weird at the same time when you're trying to piece all the elements together. So what does this come to? Well, it just means that there's lots of different ways to project the Earth, but there isn't just one perfect way. Well, that's not true. There is, the globe, but you're not carrying a globe around your pocket everywhere you go. So we have to decide, do we want the area to be right? We want the shape to look right? How do we project this? Or do we, especially when we're trying to make a smaller map, you want to make a map of just North America. What projection would be best for that? Well, North America, we could do one using a planar projection because it's just that one zone. Or we could do also looking at a conic projection because that would make sense too, because if we're just going to look at one area that covers a very small area of latitude, we could do it that way as well. So lots of different distortion. So I bring in the word distortion. This is distortion. I love this. Well, I don't love this, but I love this image because we've seen that. People distort their face because somehow they feel that this makes it better, and then when they don't do that, then you're very, I think the phrase is catfished. You're quite surprised because that's not what the people look like. And I've seen everybody do it. There's no line that's drawn of a particular type of person. I've seen everybody do it. But what you're doing is you're actually changing the integrity. So these different maps, these are different projections, and what they've done is they've used the profile of a face to show where would the distortion be. So here's what it should look like. This is the most accurate here. Then look at how skewed that face becomes. I think my favorite, I have two, would be sinusoidal, because it's fun to say, which is this one right here. And another one would be the Robinson map. The Robinson map is the map that you grew up probably using going into a K through 12. It's that map they pulled down. It was this weird shape. I reference it as the Mrs. Robinson map because I consider it the feel-good map because everything is there. It makes you feel good that everything is there, but it's not accurate at all. There's so many distortions involved that you lose a ton of the integrity. But for a K through 12, you're not plotting using push pins your journey to travel across the sea. You just are trying to learn the different names of the countries and what they're next to, and that there's bodies of water in between them. But these are all different types of projections. That being said, can I was going to ask a question, but the statement is you can use maps to confuse people. Cartographers have the ability to take this information to mess with your mind. Here's two as an example. I'll start with this one. So this, as you can tell, is all of Africa. And what they've done is they've put all these different countries to put in here to show in perspective how big Africa is as a continent. This is one of my favorite maps I saw. This is bad projection number 358. Oops, all South Americas. This is an entire map. These are all South America. Funny, huh? It looks good. At first, you probably thought it looked fine. Because I know for a split moment when I first saw it, I was going through like a comic thing. And I was like, something's not right about that. Because it was smaller. But I was like, oh my gosh, how funny is that? I don't know. So that's one way we look at it. So we looked at latitude, longitude briefly. We looked at the projection system. So let's look at one more. It's called the Public Land Survey, known as Township and Range. This isn't often used in most academia, but I continue to teach it because it's very prominent where I live, looking into outside of Santa Clarita, Palmdale, Lancaster, looking in the Mojave Desert, stuff like that. We certainly still see it. So as part of the land ordinance of 1785, where settlers could purchase farmland and move out west, they needed a way to really mark out the unknown territories. So Thomas Jefferson wrote the resolution, which led to the Homestead Act of 1862. And what it did is that we knew that there was land out there, but we didn't know how much. So we weren't going to try to mess with a normal grid system of latitude and longitude. We wanted to break things up into 40-acre parcels. So we wanted to create a system of X and Y axes so we can really see what's happening in the land. So that's what we have here. So the way this is observed is, oh, that's really blurry. You have your baseline and your principal meridian, and then this is broken up into a grid system, really a lot like Excel. But the problem is that each one of these boxes is 36 square miles, so it's pretty large. So we can take one of these boxes and we can subdivide it into smaller sections. These are the sections. These are 1 mile by 1 mile square, okay? And if you notice, I call it the snake method. It's numbered weird. It starts in the top right and then goes back and forth. All the way down to 36. So you could say that, oh, I want to live in this section, which is section number 15, which in this case is found in the Range 2W Township 3S. So what does that mean? Well, our ranges are columns, townships are rows. So this is your principal meridian. This column is range 1 east, range 2 east, range 3, range 4, range 5 east, range 1 west, range 2 west, so on and so forth. These are going to be townships, township 1 north, township 2 north, and so on and so forth. So we're able to pinpoint a location. Then each one of these boxes can be subdivided into quadrants. And these quadrants break down into 40-acre parcels. So the way that quadrants work is that you obviously have your north, south, east, west, perfect. But then the quadrants are the boxes that were made. So you have your northeast quadrant or your southwest quadrant. So to really simplify this, think about how when people ask where you live, you start usually small and you work big. So someone says, well, where do you live? And I go, well, I live in Val Verde, which is this little box here. And they'll go, well, where's Val Verde? Well, Val Verde is part of this bigger box, which is, we'll say, Castaic. Well, where's Castaic? Well, Castaic is part of unincorporated Los Angeles, part of the Santa Clarita Valley. Well, where's that? It's in Southern California. Oh, I know where that is, right? You ever do that? I don't know. I mean, I always, where do you, Santa Clarita? Six Flags. I don't live at Six Flags, but it's close enough. So this is that idea. So what we would say is if this is my box, I'd say, well, I lived here. I live in the southeast corner of this quadrant, which is the northwest quadrant, which is part of section number 25, which is part of Range 2 West and Township 3 South. So I'll do that again. I'll do the same thing so you can see it. I have additional videos in the modules to kind of walk you through it, but it's just something that I like to talk about because, especially in my normal face-to-face classes, because we see this, and I'll talk about how that looks in a moment. So I live in this box. This is in the south, and look over there, okay, southeast corner of the northwest corner of section number 25, Township and Range. So why is this working like this? Why is everything in blocks? Well, if you've ever driven out the 14 Palmdale Lancaster, you'll notice that everything is set in letters and numbers. You know, Avenue I, street number 123 West. That's exactly what this was about. Though Palmdale Lancaster was a very large, broad, flat area. There's some volcanics and stuff, but and the San Andreas Fault that runs right through it. But how do we map off this huge area into a very simplistic grid system that makes sense? Think about when you're driving on the freeway. Oh, we've got 40 acres available, 80 acres available, because things were still divided up into this. If you get into real estate, you'll certainly see this too, how things are broken up into this township and range piece. So there's additional pieces on Canvas for you so you can use that. But again, very quick, I know we covered a lot. We covered latitude, longitude. We covered projections, and we covered township and range. So a lot of different elements. But nonetheless, I hope you enjoyed this. Don't forget to subscribe and to check out some of the other videos, and we'll talk soon.